Logarithms are one of the most abstract and weird concepts I have ever seen in math. And I mean, I'm a math major. This is the one. There's a couple of concepts in trig that are really tricky. This is the hardest one. If you can handle this, at least if you can understand this, you'll be fine. Because like this is like as hard as it gets. So just a bit of warning going in. If it feels like at part of the way or at the end of the lesson that you're like, I don't get it, please don't freak out. Give me a couple days to work with it. Okay. Basically, logarithms are the last 3 lessons. Today we're going to talk about graphs of logarithms. Then sometime next week we're going to talk about what are called the laws of logarithms. Basically, that's like algebra skills you can do with them. And then finally we'll talk about how to solve things involving logarithms. But just so you guys are forewarned, it's a weird concept. So I'll do my very best, obviously, to try to explain how logarithms work. So I'm going to start kind of at a very odd place. This may seem, why are we starting here? I promise I have a point, okay? So I'd like to graph y equals 2 to the x. And I'd like to not use our calculator. Let's just try graphing it by hand, because you should hopefully know roughly what it looks like. So where are some of like the key kind of points? There's actually really only one really key point on an exponential graph. Yeah, you guys mean the y-intercept at 1, right? That's pretty much universally a point on any exponential graph, as long as you don't like transform the graph somehow. And then other than that, I guess I can plot this one at 2 and this one at 4 and this one at 8, and these ones form an asymptote. So I'll just underline this guy in purple because I can do multiple colors. If you guys have a different color, you may want to use a different color for the next half. You guys remember the concept of an inverse from earlier, right? Inverse means flip x and y around. Okay. Mathematicians have known that inverses exist for a long time because it's not hard. All you do is you just take the graph and you kind of like turn it sideways. Right? And so we should be able to graph x equals 2 to the power of y. So I'm just going to kind of draw a dotted line right here. You know how I asked you earlier for a key point? Where would that key point move to in this particular graph? So this point right here was a y-intercept of 1. If you flip x and y around, it's no longer a y-intercept of 1, it's now an... Good, yeah. So the one key point I would have would be right here. And then I'm just going to kind of do this by sight to some degree. Let me know if this doesn't kind of make sense to you. This would kind of go up like that. And this would kind of go down like that. Would you guys be able to agree that like visually I've flipped the graph that little sideways kind of inverse thing? Okay, so mathematicians have known that this graph in red, they know that it exists. Clearly it exists, I've just drawn the graph. Is it a function? What makes something a function? That's probably the best way of looking at a graph. Yeah, vertical line test. So is there ever a point where you're getting a vertical line and you're getting like more than one time that it crosses? Although this line right here is getting very steep, technically it is kind of going still slightly off to the side. So this is a function. Let's talk through the properties then of this red graph. There is now an x-intercept. It is at 1 and 0. Is there a y-intercept? Doesn't look like it, no. Is there an asymptote? Be more specific, not just 0, but what is 0? Yeah, x, I guess I'd say x can't equal 0. I prefer that notation. If you wrote x equals 0, I wouldn't mark it wrong. My personal preference is to tell you what it can't be. What about the domain? Can you use anything you want for x? What's the lowest number for x you can use? That's a bad question. What, not including itself, what is the lowest number for x you can use? Yeah, you can't use 0, so x has to be greater than 0. And your range looks like it actually can be anything in the world you want it to be. It looks like it could be element of the reals then. Okay. This is actually a very applicable graph in a lot of different settings. I actually didn't realize this until I had kids. I want to show you, I wish I had taken a picture of it. This won't make sense because you guys have kids. But when I went for my daughter's checkups at the doctor's, they actually plotted her, how did it work again? This was her age on this side right here on a graph. And this was her, I think it was her weight. And so when Cammie or Kinsey was born, when she's born at age 0, she weighs a certain amount. Right? And then as she gets older, she gets heavier and she gets heavier and she gets heavier. But what ends up happening is she shouldn't continue to get heavier at a linear rate. Because otherwise, at some point, my daughter would weigh like 900 pounds. Does that make sense? And her weight kind of slows down. And for me, this all of a sudden was like, as a math person, I was like, whoa, there is a logarithmic graph. Because they actually plotted a graph that looks something like this. And you know it's not perfect, but that's basically what happens right here is the graph is going to start and it's going to get bigger, but it kind of levels out. Does that make sense? No, because I mean, if this were her and her weight, this would be her getting heavier very, very fast. That'd be bad, right? And if it was linear, like say the dashed line right there, when she becomes 100, she'd weigh 100,000 pounds. That's also bad, right? But at first, when you're really young, you should hopefully put on weight quite quickly, right? She goes from being 6 pounds to 10 pounds in like 2 weeks. And then she goes from being 10 pounds to 12 pounds in another week, right? But then eventually it slows down. And like my daughter hasn't gained weight really now in like 6 months. Like she's kind of steady at like 28 pounds or something. Does that make sense? Okay, I got off topic here. This graph right here, we've known about it for a long time. Here is the problem, and I hope that's what my next slide is. How in the world do you isolate the graph x equals 2 to the y for y? It's a huge problem for mathematicians for years. Because, like, for example, let's say I gave you the graph y equals 2x. No, that's a poor example. Let me try again. Let's say I give you the graph x equals 2y. Not 2 to the power of y, but 2y. How do you get y by itself? Well, you just divide by 2. That's not hard to do, right? Or let's say I gave you the graph x equals y squared. You just square root both graphs. Does that make sense? The point I want to make here is, how in the world do you take a graph where the exponent is y and get it by itself? Now, there is actually one solution, but it's not a good solution. You could take the y square root of something. That makes sense? Like, if it was a y equals x to the third, you could take like the third root of both sides. So therefore, since you have 2 to the y, in theory, you could take the y root of both sides. On this side right here, if you take the y root of 2 to the y, you'd be left with 2. But then the problem over here is then you have the y root of x. And I'm not sure that that actually made it better. It's valid, but it's not actually useful. So mathematicians then, and this sounds weird, but mathematicians invented logarithms to solve this problem. And I like that word invented because it doesn't seem like math should be something that you like invent. Does that make sense? But like they had to create a new mathematical operation that helps us solve this problem. Logarithms are an operation. Okay? For example, just like adding numbers is the opposite of subtracting numbers, and multiplying is the opposite of dividing, and squaring is the opposite of square rooting, logarithms were developed to be the opposite of exponents. Not exponents like, you know how when you square you have to square root, but we're talking about when the exponent is the variable. That's why logarithms were invented, basically. So it's a new operation. Now you guys actually have a little bit of experience with logarithms from chemistry. Do you guys remember pH formulas? Okay. There's actually two things. My grade 11's right here, actually. Hopefully remember them. What's the formula for pH? You guys remember?
H3O.
Negative log H3O. you remember the other formula? Do you guys remember it? You got it there, yeah. To find H3O, it's 10 to the power of negative pH. Now, last year when you guys learned these, and for any of you guys back there listening, not that it matters to you now, but when I teach you guys this in chemistry, I just kind of tell you to do it. But now I can maybe explain a little bit better as to how those formulas work. I know you don't remember them probably, but the opposite of a log is an exponent. You guys see how up here the exponent is your variable? These guys are opposites of each other. Logs were developed then to help undo exponent variables. Does that make sense? If you can wrap your head around that, you're good. Because that is a very foreign concept. Okay. So here's what they developed. Okay. You need to write this down somewhere or memorize it. This is kind of like the fundamental idea behind logarithms. Let's say you were given y or x equals b to the y. And I ask you right here, get y by itself. Can you get y by itself? Well, not without someone developing logarithms. Here is what it's equivalent to. Y equals log with a small b to the x. I'll get to that in a second. These two things are equivalent to each other. So I would say, like, you know how I gave you guys a formula sheet a while back? You probably should start using it now. We're gonna use it over the next couple of days. Write this down somewhere on there. So if you're given x equals b to the y, hopefully you guys are with me when I say you can't isolate for y. It's just there's no known way to do so up until now. Does that make sense? You can't get y by itself. So to solve this problem, logarithms were developed, and it was just determined that this is how you get y by itself. We're going to get y by itself by taking log with a little b down here of x. And my goal now for the rest of the class is to try to walk you through what the heck does this mean. Because that's going to be the foreign part, where it's like, well, what does log mean? So I'm going to make up an example here. Actually, I'll use the example I have in my notes here. Let's say you were given y equals 2 to the x, like this graph right here. But let's say I asked you for its inverse. The inverse of the blue graph would then be x equals 2 to the y. That would be this graph right here. Does that make sense? It's actually the one we started class with. This red graph right here is actually x equals 2 to the y. I know the graph exists. I even showed you that there's a purpose behind it. It's a useful graph. It is a function. But can you type this into your graphing calculator? No, you can't. So an equivalent form of writing this would be like this. You write the y that was up in the top corner. We want it by itself, so we write that y by itself. Okay. Then you take a log. Okay. You know how this 2 right here is called a base? Because it's like the low part of the exponent? Okay. Well, we put a little 2 down here, and this 2 is also referred to as a base. So when I talk about this, this is called log base 2. And then the 2 just refers to the fact that it's actually this 2 right here. And then for the last step, whatever this side of the equation here was, which in our case was x, that's what goes right here. These two equations right here are equivalent to each other. The top one, though, you cannot type in your graphing calculator, but the bottom one you can. Does that make sense? Okay, grab a graphing calculator. I want to show you how to graph this. Okay, so can you type in x equals b to the y? Not physically possible. I know that graph exists. Clearly it exists. I just drew it. I told you that it measures my daughter's weight when she's little, right? But we can't type it in our calculator. So this was developed as an equivalent expression. So you need to use this log button right here. Here's the only problem. On calculators, there should be a little number right there where my cursor is. That should say a 2. And the default setting on your calculator is to always do a base of 10. Okay. You guys remember how, like, when we did, I was talking about pHs a minute ago? There was no number sitting right here between that log right there. If it does not give a number, the default is a 10. And that hopefully makes sense because this 10 right here is equivalent to that 10 right there. So, to be honest, the log button in our calculator is not useful. I need to actually show you where to find a different log button. You have to go second, catalog. And then it wouldn't hurt to go, you got to press L, whatever the heck L is. And then you got to scroll down and try to find where logs are. Now, my calculator, unfortunately, is one of the older ones. Mine just literally gives log. But if you have a newer one, so sorry, Brad, and anybody else have one of the older ones? Well, no, you have an 84, right? Do any of you guys have one that says like log with like a little number down at the bottom there, or it says like log base something? Okay, I won't be able to show you guys this because my calculator up here doesn't do this, but pick log base. Okay? Brad, I'll talk with you in a second about how to fix yours. Okay, and then what should be able to happen is you guys should be able to go and like throw a little 2 down here in the corner. Is everybody able to find that one in their calculator? Okay. Brad, I guess I'm talking just to you here. Here's how we solve this. You take log of x because the x is what we were logging. And then in order to get the base to show up, what we're going to do is we're going to divide by log of 2. And 2 is your base. And it essentially is the same thing. So that's kind of this cheater way of doing it. And I'll show you why later. So if you can't do log base 2x in your calculator, you can do log x, and then you divide by log 2. And those are equivalent. So, okay, let's graph that. Let's see whether you guys... Oh, hang on. We better change our window size. At least I better change my window size. You guys able to get a graph that looks like this? This is a logarithmic graph. It is kind of like a flipped exponential graph. I'm just going to throw in the exponential graph just for context. That would be 2 to the power of x. You guys see right here how the 2 to the power of x graph kind of just takes off like a rocket this way? Well, a logarithmic graph kind of does the opposite. It starts very, 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 very steep in the negatives. And I would say most of the time for real world applications, we don't actually need it to go in the negatives. But where the real world applications are useful is it's a graph that keeps going, but it's like it's slowing down. That's a logarithmic graph. It's where something needs to actually kind of level out after a while. Does that make sense? Okay, so back to the screen here then. Here's some properties then of most logarithmic graphs. It has a horizontal asymptote at x for 0. There's always an x-intercept right here at the number 1. X always has to be greater than 0, and the range is anything you want. There's a huge similarity between this graph and a square root graph. Because you remember how a square root graph, you can't square root a negative number? Logarithmic graphs, you cannot log a negative number. I want to do a couple of tests here. If you were to go to like a regular screen and try to log some numbers, I can log 2. I can log 500. But try as I might, it is not possible to work with negative numbers in logarithms. Why? Okay, that's a hard question. We got to traipse backwards a lot. in a log graph, I'm asking you what x is right here. So I'm asking you to try to plug in a negative x value. But keep in mind, what were logs developed to do? Logs were developed to try to explain the fact that we were actually inversing a exponential graph. Okay. So look at an exponential graph. This blue one right here is exponential. Now, normally I'd ask you, well, what x values can you have on this graph? But keep in mind, when I'm asking you about x values were actually changed to y values. Does that make sense? So on the blue graph right here, can I find a y value that's negative? No. Right. An exponential graph in blue does not have a y value that's negative. Therefore, a log graph, which is flipping x and y around, if this graph cannot have a negative y value, this graph right here cannot have a negative x value. So in terms of logarithms, you can use any numbers you want so long as they're not negative. Or, by the way, you can't use 0. If you want to test that out, you cannot log 0. Okay, so that goes back to like one of the fundamental questions of the class then. What is a logarithm? A logarithm is a mathematical operation. Okay. In your heads, you guys know how to probably do, like, say if I give you the number 2 and I ask you to add 2, you can do that. 2 plus 2, you can do that. If I ask you to do 2 times 2, you can probably do that. If I ask you to square 2, you can probably do that. If I ask you to square root the number 2, although you probably can't do it in your head, in your brains, you probably understand that that's a number. Does that make sense? Logs are the exact same thing. They are an operation, but they're the operation that undoes an exponent. Does that make sense? So I'm going to say this a lot over the next little while. Whenever you see log of something, don't freak out. It is just a number. Like when you get told the log of 3, it's just a number. It's just what it's asking you to do is it's asking you to like uninverse / like undo the exponent. That's what it's doing. Does that make sense? Like I said, it's a very abstract concept. Like it's very different. If you can understand that, that's fantastic. I don't want to say that you shouldn't understand that, but at the very least, what I'm going to talk about now, at least if you can do what I show you how to do, then you'll still be okay. But if you can understand why we're doing it, that's probably better. So here again is that exact same information then about how to convert an exponent to a log. I just use different letters. If you have like a base to the y equals x, this thing right here, you cannot get y by itself for. So rather than trying to write this, we write the y by itself. This base right here is the little number that goes next to the log. And what it was supposed to be equals, that's what we're actually going to do the logging of. Okay, so let's do some examples. Let's try to graph this thing here. Except let's not use our calculator. I know we can use our calculator. We'll do it after we try it by hand. This is the graph of y equals log base 3x. What else is it equivalent to? So like if I took this notation, can I write it in the other way? It would be x equals 3 to the power of y. It would be equal to a graph which we weren't able to type this in our graphing calculator anyways. Now again, I can't really graph this one here, but could I graph its inverse? That would, the inverse of it, I'm going to do that in blue. The inverse of this guy right here would be y equals 3 to the x. Do you guys know what y equals 3 to the x would look like? Sure, it would look like any good old-fashioned exponential graph would have looked like. Okay, but blue is not the graph I actually want, though. Does that make sense? I'm only graphing blue to get some perspective here, because then I'm going to draw like the dashed line across the middle here. So in red, I'll draw what the inverse of it looks like. This point will come to right here, and it'll look like this. You know what the difference is going to be? You know how this blue graph right here was going to be a lot steeper than like a 2 to the x graph? It just means that this section right here is not going to rise quite as fast. That's all. That's what this 3 right here does. The bigger this number right here means like the slower this graph gets bigger. Because in blue, the bigger the exponent, the base of the exponent, the faster that graph went up. Well, for this graph, it means the slower it goes up, that's all. How does it affect our properties? Honestly, it doesn't. Like, they're all still the exact same. Your x-intercept is at 1. You don't have a y-intercept. X can't be 0. Not only that, it actually has to be positive. And your range is everything. Long story short, all logarithmic graphs pretty much have the same sort of shape to them. They start very steeply from the axis, and then they slow down very rapidly. How rapidly they slow down is dependent on that number. Does that make sense? Lost my little cursor thing. Okay, you guys know how you can have an exponential graph that goes downhill? Like, for example, this red graph right here is going downhill. We call the red graph here decay. Well, you can also have a decaying logarithmic graph. And that would be what we have right here in blue. This blue graph right here is a decaying logarithmic graph. Basically what's happened is, rather than starting low and getting slightly bigger, a decaying logarithmic graph also still goes down, but it starts high on the asymptote and then slowly but surely goes lower. Does that make sense? So if you ever had a base down here that was like a fraction type number, like 0.5 or something like that, it's going to cause the graph, rather than to start low and go up, we'll actually start it to start high and drop down. Okay, so based on that, again, let's try to do this without our calculators. Can you use your calculator? For sure, you can. But I mean, my goal here is to try to build the behind-the-scenes skills. Let's talk about what this graph might look like then. Do you know what a generic log graph would look like now? Hopefully. It's going to start like this and do this sort of shape. That's what a generic log graph does. But now we're going to do some transformations to it. What's the negative in front going to do? Flip it. Head over heels, like, we should say we've been reflected over the x-axis. So that means that now it's actually the exact same as what I just showed you. Basically, it's like a decaying log graph. So that's what the negative did. So if I want to just put a little note here, that's what the negative accomplished. What's the plus 2 going to do? Move it up 2. What's the plus 9 going to do? Move it to the left 9. Well, that's going to move your asymptote, though, by the way. Because remember, your asymptote right here is at 0. So now we're going to have an asymptote over here at 9. The graph is still going to come down, but it's basically going to start moving like that. Does that make sense? Because like I'm moving it up as well. So you know how you used to have a point right here on the axis? That point is actually 2 units higher right now. Because you used to have a point right here that was a very critical point. Your x-intercept has actually been moved up 2. I mean, the graph is still slowly but surely, you know, going that direction here. It's just it's slightly higher. So now let's grab our calculators and see whether you can graph these things. So go to y equals. You'll have to do negative first. Then you guys are going to have to go second, catalog. You're going to have to look for the log base one, wherever that is in your particular calculator, unless you don't have one of these ones. So I don't have a log base one. So then what I'm going to do, so Brad, for you and me here, I'm going to do bracket x plus 9, close the bracket, then divide by log of 3, close that bracket, and then afterwards I add 2. Does that make sense to you? Okay. So hopefully when you graph this thing, you guys will get something that looks like this. Okay, a couple of notes here. This is going to look very similar to a square root graph. It has a very similar concept to it. However, a square root graph literally just starts at a dot. That's not what happened here. There is not a point right here that this guy started at. There's an asymptote where the graph has actually gone very, very steep all the way up to infinity. But your calculator probably can't handle drawing a line that steep. So make sure that when you guys use your calculator, make sure you interpret what it means. The graph is not just randomly starting at a point right here. The graph is starting all the way up here and working its way all the way down and over. So there is not a start point to this graph. Is that clear? Okay, why don't you guys go take 5, because I've still got so much more to cover. It's such a big topic. It is. Wait, how am I doing so far? I need feedback. Driana says good. Any questions? This is one of, just so you guys know, for me, this is one of the hardest concepts to teach. Like, it's not an easy concept for me to teach. So if it feels like it's hard for you to learn, I said that earlier. Like, logs are the bane of most people's existence in math. They suck. So. Okay, here's some more pictures just kind of talking about transformations you could do to graphs. Why don't we try to talk through what it looks like has happened? I know you guys don't have color on yours, but if you can look at mine. Okay, so here's the red graph. How has this red graph turned into the blue graph here? Any ideas? Everything has been shrunk. Okay, so there's a couple things you could do. You could make it y equals log, and then whatever the base was, we could just take this thing and make it like a, well, actually, no, that's wrong. We could put like a 1/2 in front of it, maybe. Does that make sense? We could shrink it down. No, because the x-intercept would still be squished down. Yeah, so I think this is actually a 1/3 actually, because as I look at this, you see how this point's right up here at 3, and now it's down there at 1. So what's happened to this graph is we've put a 1/3 in front of it, and we've squished it down. Does that make sense? What about this graph here? Anyone notice something about it? Every single point has been moved up. You guys see that? So how do I write that? It looks like it's going up by 1. So I want to make sure I'm really clear here. You need to first close the bracket for x, and after you close the bracket for x, then you get to add 1. It would move it side to side. Make sense? Yeah, you know what, actually, this next graph right here, I guess, to be honest, it looks the exact same as the one we just did, doesn't it? Doesn't it look like the blue to purple is going up by 1 again? Yeah. I don't know. I pulled this out of a book somewhere. You know what, let's skip to this one right here, though, because this one has a point I'd rather make. Do you guys see how the asymptote right here has been drawn in? How do I account for that, then? This whole graph has been shifted over.
That would be
In the brackets, yeah. For those of you guys who were kind of saying that, we need to go x minus 4 in the brackets to shift the whole graph over, asymptote included. I said to you guys in the first unit, I promise you by the end of the year you'll know all of these transformations, because we're still going to keep using them. Right? You throw a 2 in front, it makes it taller. You throw a 4 inside, it squishes it in. Like, at some point, you will need to know these, because we do them all the time. Like, it doesn't go away. Okay, here I found a slide that just kind of talks about all the different things you could do to a log graph, and this is intense. So let's see that I can walk you through little by little. If you threw a number in front of a log graph, it would take the graph and you would stretch it up and down like this. If you threw a number inside the brackets next to x, it would squish it in like an accordion. Does that make sense? Be careful about factoring. If you had it in factored form properly and there was an h like subtracted, that would move it side to side. And then after you close all of these brackets, if afterwards there's a plus number, then it goes up and down. Okay, let's go on to something where we can actually do something. Because to be honest, most of that was just drawing graphs. And although that is useful, I want to work on some skills as well. I'd like to try to change these from exponents into logarithms. So like, for example, let's say that I gave you this as an equation here. I know there's like n and x. But let's say I asked you to get x by itself. Can we get x by itself? Do you guys remember the method of changing exponents to logarithms? It'll be log with a small base of 4. Because see how this guy right here is the base of the exponent? That base is what we put right here. It's now going to equal x. And the log that we're going to take is going to be of n. This is the way that you'd rearrange it. Okay, let's try another one here. What is the base of this equation right here? The 3. 3 is the base. What is the exponent of this equation? Okay, the reason why logs are developed is because exponents we can't get by themselves. So now I will get it by itself. And then the last number, the number that you are actually logging, I think that's a verb. I don't know, I'm making up words here. But like the action that you're taking is you're logging a number. The number that you're logging is 243. This we can actually test in our calculator, by the way. Grab a calculator. However it is that your calculator works, try to find a way to type in log base 3 243. So for most of you guys, you have to find the one that has the base. For you two, it would look like this. You'd go log of 243, and then you'd divide by the log of 3. And if it works out properly, this better equal the number 5. And hopefully, however your calculator works, does got you 5. That makes sense? Okay, one more. What's my base of this guy right here? 2, I guess, yeah. So it's a log with a base of 2. Then what is the exponent that we were trying to get itself? No, the exponent is negative 4. So the exponent goes over here. And then the 1/16th is actually the thing that you are going to log. So again, you guys could actually test this in your calculator. You could, however your calculator works, type in log base 2 of 1/16, and hopefully you'll get it to tell you the answer is negative 4. I'm going to say this a lot. When you log a number, it's just a number. Logging is an operation. It's like a taking down trees operation as well. But yeah, like a log is a verb in math. All right, let's keep going here. Let's try to change these from log form to exponential form. So these are written as logarithms. So I'd suggest start with the base. The base is 10. 10 to the power 4 would equal 10,000. Does that seem like a true statement? Sure, shouldn't it? 10 to the 4 should be 10,000. Or the next one, the base is 5. We're going to make it go to the power of negative 2. And that should then equal 1/25. So this 5 right here is your base. This guy over here will be your exponent. And it's going to equal the 1/25. Again, is this a true statement? What does 5 to the minus 2 mean? Well, 5 to the minus 2 means 1 over 5 squared. 5 squared is 25, so that fits. Okay, let's try it though without numbers. What's your base? Okay. the exponent is going to be this x right here, which now is by itself, but previously it would have been up here, unable to get by itself, and it would equal t. Years ago, I had a student who figured out that it kind of works like a 7. I don't know if this will help anybody, but treat it like k, x, t, and it kind of becomes like a 7. Go k to the x, giving t. There's like a 7 kind of drawn there. I don't know if that helps at all. But. Okay, now let's try to evaluate. That means answer. Now, technically in your calculator, you should be able to type in log base 264 equals x. So for those of you guys who have your calculators nearby, can you tell me what x is going to be? 6. Now, you guys know how to use a calculator, but one of my goals is to try to explain to you why the answer is 6. Because I'd like you not just to default to your calculator, it said it was 6. So I want to try to explain why it's 6. How else could we have written this log notation? If it helps, look at the 7. 2 to the power of x should equal 64. 64, though, can be written as 2 to the 6. And the 2's cancel, therefore x is 6. Now, granted, I don't need you to do that when you solve this question. I would just ask you to type it in your calculator. But I'm trying to further your understanding as to what it is doing. Because that's what a log is doing. The work we just did there is what your calculator was able to do as a machine. Much faster than you were, obviously, right? But I want you to know how. So let's try this next one again. If you have a calculator, type in log base 4 of 1 over 16. You should be able to tell me what it is as a number just purely using your calculator. -2? Yeah. Okay. Again, for functional purposes, if you can type it in your calculator, you're probably good. But for understanding purposes, let's try to rearrange this guy right here and see what it would look like. So you would start with the base of 4. The base of 4 would go to the power of x, and it would equal 1 over 16. I can write both of these things with common bases. Would it make sense to make 4 equal to 2 squared? And 16 is actually 2 to the 4. But because it's on the bottom, it's actually 2 to the -4. Is it able to say that? And the whole point here being that you can then cancel the 2's. You get 2x equals -4. You divide by 2. You divide by 2. And that's where we got x equals -2. That is what your calculator did. So if you're wondering why the calculator works the way it does, that's what it's doing. Okay, one more time. If in your calculator you do log base 749, anyone get an answer? 2. Okay. What did your calculator do? It went 7 to the power of x equals 49. Then it recognizes that 49 is actually 7 squared, canceled the 7's, and said, hey, x equals 2. How am I doing? You guys able to follow this? Awesome. Okay. Oh my goodness, I got so much more to do here. Okay, one more example, and then we got to do the word problems. Yay. Word problems. Okay, let's do this one a little faster. Can you type this in your calculator and solve it? Kind of. I mean, you can type in log base 5x, but x in your calculator is already predefined as something. So on the questions like this, you can't actually really use your calculator. But we can use our understanding of how logarithms work. We can say, well, this really means 5 to the -3 equals x. That makes sense, using that kind of 7 kind of concept, if that helps. 5 to the -3 equals x. Okay, well, I can do 5 to the -3 in my calculator. That's 1 over 125, or 0.5 something. Whatever it is. That makes sense? Or let's try this one. Your calculator is not actually helpful here. But your knowledge of logarithms is, this really means, anyone want to give it a shot as to how to rearrange this guy? Fantastic, good job guys. Therefore, to solve for x, square root both sides, x equals 6. Or this last one, again, you really can't use your calculator, but you can say that 64 to the power of 2/3 equals x. That one's a bit challenging. Do you guys know what 2/3 means as an exponent? Okay, it really can be written like this. 64 can be written as a 2 times a 1/3. That makes sense? 2/3 is really 2 of 1/3. The 2 means to square. So if you guys have a calculator, this is going to be a large number. I can't do it in my head, but can someone tell me what 64 squared is? 4096. Okay. So I've taken care of the squared, the top part of the fraction, but I still have a 1/3. What does a 1/3 mean as an exponent? Anybody know what a 1/2 meant as an exponent? Jessica, do you know it?
It's like the one.
Because they're doing it right now. The 1/3 is a square root or a cubed root. Does that make sense? So because it's a 1/3, we need to cube root 4096. We would have done this last year. That's why I was looking at maybe them, because they're doing it right now. So if you got your calculator, can you cube root 4096?
60.
There you go.
I just did like 64 to the power.
Okay, and you physically could go in your calculator. You could actually cheat and go 64 to the power of 2/3. That'll work. Okay. I just wanted to explain what it's doing. Okay. So. Okay, let's move on here. I'm taking too long on this. Okay, so let's try some. Now that I've talked about the basics of what logarithms are, which again is a mouthful on its own to try to know how they work. Now we need to solve some problems. Okay. So we'd like to try to write some equations. Let's say there's a horizontal asymptote of y equals 2, a y-intercept of 5, and a base of 2, and we want to write an exponential function. So y-intercept of 5 would kind of be like right about there. A horizontal asymptote of y equals 2 means that you'd have like an asymptote there, and it looks like you're making it go up like that. Finished? Here, just hand it to me. I'll mark it, try sometime over the course of the day. Thanks. Okay, this is an exponential function. I told you the base, though. The base is 2, so it's 2 to the x. How do you get that asymptote up to 2? Yeah, plus 2 at the end. That'll move the asymptote up 2. Where is that y-intercept going to be, though? Well, okay, if it's supposed to be at 5. It's usually at 1, but now you moved it up 2, so it's at 3. How do we get it the rest of the way up to 5? Any thoughts? What number should we put right here? So if we left the number 1 right here, if we just looked at this section right here, the y-intercept would be at 1. That makes sense? But then the plus 2 would move the graph up more, so it would be at 3. So what number do we need to put right here instead of a 1? 3. Because that 3 would make the graph become 3 times taller, so your y-intercept of 1 would now actually be up at 3. But then when you move the whole graph up 2 more, then rather than it being at 3, now it would be at 5.
I was thinking of it like starting at 3 and then going up.
Does that make sense? Did you suggest you wanted a 2 there?
I don't know. I was thinking that we were starting at 3 and then I was just like finding a number that went from 3 to 5.
What we really need to do is we need to find a number that gets it to 3, so that then going up 2 more then gets it the rest of the way to 5.
I was going like reverse.
Fair enough. Does that make sense? Okay, let's try the harder one. We're going to try a logarithmic graph. So first I'm going to try to sketch what this looks like roughly. It has a base of 4. It has a vertical asymptote of x equals minus 2. And I'm going to tell you actually a point that it goes through. Yeah. So it goes to 2, negative 3. So that's somewhere around here. 2, negative 3. So that looks like it's doing something like that, I guess. That's my logarithmic function. That's my equation for it. Okay, so to start, I'm going to write y equals log. I'm going to leave a lot of room on both sides. Okay, I told you what the base was. So I can put a little 4 sitting down here. Does that make sense? How do I deal with that asymptote? Good. Inside the brackets, you're going to need an x plus 2. Good job. Does that make sense to everybody else? Here's our problem. At this point here, how do we force it to go through the point 2, negative 3? We need to do some sort of, maneuvering. And we've done this before. We need some sort of a value out front, I guess. That's going to somehow, like, compress it to get it through the spot we want. Does that make sense? How am I going to find that a value?
Point.
I gave you a point for a reason. Okay, so let's try that. Negative 3 is y. We don't know a. It's log base 4. And then 2 goes there. Now, I'm going to say this a lot over the next little while, so I may as well start today. This right here is a number. I know it looks very intimidating, but I need you to forget the fact that logs are weird looking. Log base 4 of 4 is just a number. Use your calculator and find that number. So I'm just going to write it out here. This was log base 4, technically of 4. What is log small 4, big 4? It is 1, actually, yeah. We've actually got reasons for that, which we'll talk about another day. But you could basically say then that this is equal to a times 1. So then a is negative 3. So you know what? I think I actually drew my graph wrong. I think it actually should have been probably coming down in order to get through that point. Because a negative 3 would actually flip it upside down. So I now have my equation, y equals negative 3 log base 4 x plus 2. That should meet all the parameters I need. Okay, 3 word problems, then I can be done for the day. I said this yesterday with exponents. This is the part that you're going to like the least, probably. The logs are usually better. I would say that I've never seen you have to actually write your own log equation. That's the good news. You know how like yesterday when we were doing word problems, you had to write your own equation and then solve your own equation? Typically for logarithms, you don't have to write your own equation. They'll give you an equation. The harder part, though, of logarithms is you have to be able to interpret what the heck is happening. Because they're going to give you some sort of crazy equation like this one here, or if you look at the next slides, like this one here is, oh my goodness, what does it mean? Or for this last one here, does that make sense? So most of the challenge with word problems is you got to understand what the heck is happening to the logs. So, do you guys know about the Richter scale? You ever heard about this for earthquakes? Like it measures the magnitude. If you have like a magnitude 10 earthquake, it's like catastrophic. If you have a magnitude 4 earthquake, it's not quite as bad. So, Richter scale is actually based on logs. And so what I've given you here is a formula that says a magnitude of an earthquake is equal to the log of the amplitude of the ground motion because of the earthquake divided by the amplitude of the ground motion without the earthquake. Technically, the ground is vibrating a little bit as we speak, just naturally. But during an earthquake, those vibrations are much more. Does that make sense? And so that's actually how they determine how powerful an earthquake is. It's based on how much more vibrations are there than normal. Find those two numbers, divide them, and then log it. Okay, so we're going to try to figure out how much more powerful a 6.5 is than a 2.8. So where does the 6.5 go in this equation here? It's m. Does that make sense? M is magnitude, so 6.5 equals the log, and then it's a over a0. What's the base? Good, it's 10. I mentioned that a couple times earlier today. If it doesn't show a base, it's implied that it's 10. How can I rearrange this? Well, it would be 10 is your base. It would go to the power of 6.5. And that would equal a over a0. Okay, this is getting kind of confusing. I don't really like this a over a0 bit myself. The top a stands for the actual amplitude. Does that make sense? And a0 stands for the amplitude, like, without an earthquake. It may make more sense in a question like this just to make up a number and say, well, let's just pick a number for it to be before the earthquake. And I've got a good choice of number. Let's just make it equal to 1 and just ignore it. Let's just pretend that the amplitude before we started was 1. I don't know that it actually was the number 1, but every time I'm going to use a0 from now on, I'm just going to pretend that it's the number 1, just to make things simpler. Does that make sense? So I now know that the amplitude for one of them is 10 to the 6.5. You guys have a calculator. Can someone tell me what 10 to the 6.5 is as a number? It's pretty big, obviously. 3,162,170? 270. So that number there. 77? Okay, you guys have that number though, right? Okay, so this is how much the amplitude is more than 1. So it's like 3 million times more than 1. Now let's do the exact same thing, only let's do a magnitude 2.8. So if I want to write that out, it would be 2.8 equals log base 10 of a over a0, which means it's 10 to the power of 2.8 equals a over a0. But remember, just to make things simpler, I was just saying, let's just make the original amplitude just be the number 1 just to make things simple. So can someone tell me what 10 to the 2.8 is? 930? 630. So just to recap what we've learned here. The top earthquake vibrations are 3 million times bigger than they normally would be. The bottom earthquake vibrations are only 630 times more than what they normally would be. So to answer our question, it said, how many times more powerful is one than the other? How do you figure out how many times more powerful they are? Divide them. Yeah, divide them. Because you're asking like how many times multiply. So technically you got to find the divide number. So anybody get an answer? Okay, so 5,000 times more powerful. I know it's not the exact number, but does that make sense how to solve a question like that? Again, these are frustrating because the earthquake question is a one-off. I don't know whether you're going to get a test on an earthquake or maybe you'll get a question about welders. That's my frustration as a teacher. I don't know if they're going to give you. So there's a lot to read here. Welding does stuff. N apparently is about a filter shade number so that you don't burn your eyes out, I guess. And then T is about how much light goes through the filter. I guess that makes sense, right? Like the bigger T happens to be, I guess that means that there's more light that gets through the filter. So you probably want T to actually be like a, you don't want it to be a lot, right? Because hopefully that'll keep the light from burning out your retinas or something. So looks like it goes from 2 to 14. So okay, let's go down to the bottom here. A shade number of 12 is suggested for the arc welder. We want to find the fraction of visible light. So this 12 right here, is that N or T? Based on the information they gave you. Okay, good, N, yeah. So 12 equals 7. Then you negative log t. And then you divide by 3 and you add 1. How do I solve this? Isolate for t. So before I even deal with the log, because the log on its own is a pain, let's get rid of this 1. So that means 11 equals 7 over 3 negative log t. How do I get rid of the 3? So 33, can I just say 33 over 7 equals negative log t? Does that make sense? Okay. There's also that stupid negative in front as well. I guess I could just take the negative and throw it on the other side. Okay, so good question. Basically, this is like negative 1. So what I'm going to do is I'm going to divide by negative 1. And here I'm also going to divide by negative 1, I guess. But the negative can either go with the 7 or the 33. So at the end of the day, what we have is 33 and negative 7 is equal to log of t. What's the base of the exponent? Good. There's an implied 10 right here. So to rearrange this, I would then say 10 can go to the power of negative 33 over 7. Which just means you can go into your calculator and go 10 to the power of bracket negative 33 over 7. And it'll tell you your answer. It'll be some small decimal number, probably.
That's 1.93 times 10 to the power of negative 5.
Negative 5? Everybody else get that? So that would have been the amount of light that comes through. So yeah, very little light, I guess. Which is probably good because you probably don't want that much light coming through when you're welding. That makes sense? Completely different question. But like, you need to have the skills to be able to work with logs. Here's another one. This one's about butterflies. Like I said, I don't know what you're going to get tested on. So apparently there's a relationship between butterflies and flowers. I didn't know this until I read this. Apparently the number of flowers that a butterfly feeds on is based on how many butterflies there are. Let me read that again here. In a study, scientists found the relationship between the number F of flower species. Oh, okay. So F is how many different types of flowers a butterfly can feed on, is based on how many butterflies there are, I guess. I don't know. I'm not a butterfly person. I can understand, though, that the 25 flower species is that number right there. Does that make sense? So 25 equals negative 2.641 plus 8.958, and we now need to log B, B being the number of butterflies, I guess? Isolate for B. Okay. So how do I do that? Add 2.641 to both sides, so that'll be 27.641. It'll equal 8.958 log B. Divide. Yep. Divide by 8.858. Divide by 8.958. Okay, again, what's the base? It's implied that it's a 10. So in your calculator, to rearrange this, you're going to go 10 to the power of 27.641 and divide by 8.958. That, whatever that happens to be, that's how many butterflies, I guess, there are. Like that? Okay. Whew. You guys able to follow that? So this is that 7 kind of concept where you go 10 to the power of what it's equal to equals B. That's like that rearranging chart. So that was like one I told you to write down from like way back here. This base of 10 to the power of what it's equal to is equal to X. That can be useful in solving questions. Okay, let me do a summary and then you guys can probably
No.
start packing up, I guess. We're going to start working on the assignments. Logs are intense. They're, honestly, like, that's one of the hardest concepts we have in math. Logs were, this sounds weird to say, logs were invented. Like, we had to create logs as a way to help us solve a problem. The problem being, how do you get an exponent off of the top of, like, something? How do you get it by itself? Does that make sense? So logs and exponents are very similar to each other. I need for you guys to know what log graphs look like, know their properties. I need you to know how to make logs from exponents. Like, I need you to know how to transfer them over. And then further to that, I need you to know how to, like, rearrange a log to an exponent, kind of like we did on those middle slides here, where I gave you, like these ones here. If I gave you log base 264 equals x, I need you to know the skill that 2 to the x equals 64. And then the last step is, I need you guys to know how to use them in a word problem, whatever that word problem is. I can't imagine that they would give you a question and not give you the equation. They're going to give you an equation with logs. They probably won't give you an equation if it involves exponents, but they probably will with logs. And, like, it could be butterflies, earthquakes, welders, or Lord knows what. So you need to be able to solve a word problem. Fair enough? Okay, we have 2 more lessons left, and then we're done our unit, and then we're done half our year. Yeah. All right, so you guys have 15 minutes left. Work on something, I guess. Or pack up. I don't know. Thanks for bearing with me for a really long lesson. Sorry it was so long.